Hello, welcome back. Let's get started. We are, well, 1 more minute to wait, but in the meantime, the next speaker, who is Stefan Hanke from the Karlsruhe Institute of Technology, can start to get ready. Stefan will talk about cryopumps for ET. This is going to be the last talk about the cryogenic system for the Einstein telescope. Then 3 talks about the vacuum system will follow. Stefan, whenever you're ready, you can start sharing your desktop.
Yes, okay. Let me try. So, can you see it in full screen?
Now we see, yeah, very good, very well. You can start whenever you want.
Thank you. And good afternoon, and thank you very much for the opportunity to give a short presentation here on our view regarding the cryopumping challenge for the Einstein telescope. So I'm working at KIT, the Karlsruhe Institute of Technology, and I speak in behalf of our group and will show you briefly our experience on how to design tailor-made cryopumps for special applications. So we are located in the south of Germany, and the KIT is a merger of the University Karlsruhe and the Campus North, which is the former research center Karlsruhe, and is addicted also to large-scale research. And our institute in this campus is focused on superconductivity, while our group is working in the field of vacuum. And our around 20 people are spread over all areas, so that we are able to do all the steps you have to do sequentially and in parallel for such a design job, as development of simulation tools, operating facilities to validate these developed tools, do design work on customized pumps, and all the related activities. So in general, our working area is to understand the vacuum outgassing, because this is a major field to be considered, and to deal with all different flow regimes in gas dynamics. And for all these different regimes, you need different approaches. At the end, you have different developed tools and different solutions appropriate for each situation. So as I said, when you develop tools, you have to validate them, and this is the experimental way. You establish a facility, you test your predictions, and only afterwards you can trust your simulation tools and their predictions. And therefore, we were able to develop customized cryogenic vacuum solutions for 20 years now already, including very large-scale systems for nuclear fusion. So in general, I could say a consistent description of outgassing and gas dynamics is the interplay and the key challenge in vacuum science and technology. So one could say, why cryopumping at all? So it seems to be obvious, because cryopumps are known to provide the highest pumping speed of all available commercial pumps, while cryopumping is in general based on either condensation or physisorption of gases on a cold surface. So, but why the cryopumps provide such high pumping speed? So pumping speed in general, you can easily say it is it considers the velocity of the gas. So this is more or less given by the gas we have to pump, and the temperature we have to consider of the gas in the system, and we have a capture coefficient. So this could be described as a trapping probability. So the probability that a pumping cryogenic surface will trap a gas particle after the first impact compared to the other way that it will be reflected back in my vacuum system. So this capture coefficient can change between 0 and 1. And this brings us immediately to the result that there is no much space to play with the pumping speed, except with A. A is the area, the entrance area of my pump I will use. And on the right picture, you see as long as you take commercial systems, you have to work with flanges. And this area of the flange is then what gives you this A in the equation for the pumping speed. So it's obvious that you have to go to in situ to increase A drastically and therefore to come to the capability to have a huge pumping speed. But this is not the only thing. As soon as you think on a system in situ, you are immediately free again or to play on all three subcomponents of a cryopump, on the cryogenic supply, on the thermal shield, on the cryogenic pumping surface itself. So everything can be now changed very freely to come to an appropriate system. So this is one side, to play with the design of a cryopump. On the other side, it's obvious that a well-designed cryopump can do the job as better as lower the gas flow is, which has to be managed by this cryopump. Therefore, in parallel to the design job, one has to focus also on strategies for the gas flow minimization. In ET, we know especially the outgassing will be a challenge to be considered. So having now, in general, the possibility to be in situ and to play freely with all these things on the cryopump, you come to a huge variety of cryopumps. And here I give you some examples of the cryopumps we developed in the past. So focusing on one component, cryogenic supply, you can play therefore with the supply temperature and consequently also with the cryogenic fluid. Focusing on the shield, you can have simple annular shielding or very complex multi-layer shieldings. Considering the third component, the cryogenic pumping surface, you can play, of course, again with the geometry, but also with questions, is it a simple pipe, or do I have to provide very complex and even multi-layer pumping surfaces? And on top, how the surface of my pumping surface is established. So it can be bare steel or an argon layer or activated charcoal coated panel, depending on the gas species you have to pump. So to find now the way from a challenge of a system to a proper cryopump design consists of these different steps. So first you have to define the requirement, not only available space, but gas load and all this. Then you come to the gas distribution and flow analysis, which defines at the end your target pumping speed you have to provide with the later design somehow. And for this, you need different simulation tools. I come to this in the next slides. Afterwards, it is possible to do a conceptual design, including the shieldings. And only afterwards, you go the step for detailed design, including thermohydraulics, to consider, for example, the pressure losses in all cryogenic circuits to be considered for the cryogenic supply and so on. And finally, you come to build to print design. So coming back to step 2, simulation tools, there are different methods used also in our group here. So one is mole flow. This tool is well known in the ET community. It's only dealing with the free molecular regime and considers only one gas, but has some advantages, for example, the capability to import complex designs. And in our group, we use mole flow for the design of the vacuum system of this early neutron source accelerator, a facility supporting the development of fusion-related materials. Another thing, an in-house code developed by us, developed for the ITER fusion experiment in the past, called ITERVAC, is covering the full range of Knudsen number. So all gas flow regimes, and the principle behind is to represent a complex geometry by a network consisting of all these elements represented by channels with a certain conductivity, gas sources, gas sinks, and at the end you have a simplified or a well calculatable representation of your system, which makes this code extremely fast for quick loops of design changes, try and error, and a quick outcome of a design change regarding the vacuum consequences.
We have 5 minutes left, Stefan.
Thank you. So the third thing, which is much more important, is PROVAC 3D, developed in our group. Free molecular and one gas again, but it is much more capable to consider complex geometries, because every surface is established with its individual properties. Reflector, sink, source, individual temperature, sticking coefficients, and all particles are described in real and are followed in their way. So therefore, a density at all positions in the system can be a result, and this increased computational effort is compensated by the parallelization. So now it's running also on supercomputers. Here you see an example of PROVAC, a neutral beam injection system, very complex geometry, equipped with a hypothetical cryopump, and using PROVAC 3D on the right, you come to a gas density distribution in the system for different assumed capture coefficients of this future pump. So, and if you now know which capture coefficient you need, you go then a step forward in your design. You take care for the shieldings. Here you see an example that establishing a shielding is a trade-off between perfect shielding, but then reduced capture coefficient of the pump, and heat load to be considered, and all this has to be taken into account in parallel for such a design. So since outgassing is so important at ET, we have a good experience also here, because it's also relevant. And we have an outgassing measurement apparatus measuring the outgassing of material samples in the differential method, with a sample chamber and a reference chamber for different temperatures, and enables us to develop also strategies to reduce the outgassing by testing with this apparatus outgassing before and after a certain treatment. On the left, you see the apparatus itself. On the right, some results. Outgassings for different metals, materials, stainless steel, untreated, baked, or coated, and a variety of plastic materials before and after baking to reduce outgassing and so on. Just to give you an idea of what is possible in our group. And so this interplay between our experience of design, tailor-made cryo pumping solutions for novel and challenging systems, together with our experimental capabilities, would enable us to support the ET development from our point of view. After setting pumping requirements, we could go for a design of a cryo system on the panel and the shielding side, Then we could see what are the resulting local pressures. We could take care on the aspect of water freezing on our shielding system. And in parallel, we could work on the reduction of outgassing. And I'm looking forward to start quite soon, hopefully. Thank you.
Thank you very much, Stefan. Questions or comments for Stefan? So I have a question. You probably know that in VIRGO and in LIGO as well, we currently are using cryopumps in some short sections of the vacuum tubes to basically to reduce the impact of the water vapor partial pressure. Do you already have in mind some possible applications of cryopumps within the Einstein telescope, within a large vacuum system like the one that would be the Einstein telescope?
I'm sorry, I did not catch the question. Sorry.
So if you already have in mind where you could put cryopumps within the ET vacuum system.
To be honest, we feel not familiar enough at the moment with the design to make some considerations on this. Of course, it's clear that we have to be close to the mirror because this is the most challenging section to reduce there, especially the partial pressure of water. But to come to more detail, which space is available, all the other constraints which will definitely exist. We have to start to become more familiar with the system before.
Sure. Stefan, you want to comment on this?
Yes, I would just like to add, it's probably more a question of the nomenclature. So the capabilities here for the cryopumping are needed in the what is called the pipe arm traps in the design report. So this is basically a cryopump, even though we are not having so large rates to pump there, but the quality of the vacuum must be high. And also the tools we have here available are very important to designing the thermal shields very close to the mirror. So, and to simulate the vacuum conditions. So that is, I think, shielding is cryopumping in our case.
Thank you. Any more comments or questions?
Luca?
Yes.
Just one quick question.
Oh, Fulvio.
By the way, have you tried to measure by chance the outgassing rate of mild steel, just to compare your results with the results that Paolo Piggiato have shown yesterday?
So the question is if we can measure.
If you can measure, also if you have already measured by chance mild steel.
Which steel, pardon?
Mild steel.
Low carbon
steel.
Low carbon steel.
Well, I cannot tell you spontaneously because the specialist in our group is a different person, so she knows exactly. But I will provide this information. I don't know.
That is important because since the fact that at CERN they are doing these measurements, Paolo Piggiato discussed this point yesterday. Probably the comparison will be very interesting.
Yeah, and this is not an issue. So we can, the facility is available. We can do it. It's not a problem.
Great.
Mm-hmm.
So if there are no more comments or questions, let's thank again Stefan.
Thank you.
Thank you. Move on to the next speaker, who is Antonio Pasqualetti from the European Gravitational Observatory.
Hi.
Antonio, ciao Antonio. Antonio is the responsible of the vacuum system of VIRGO. He will talk about the vacuum system of VIRGO and the challenges of the Einstein telescope vacuum system ahead of us.
Okay.
Tonio, you can share your desktop and
Sure.
start whenever you want.
Okay. Okay. I hope you can.
Yeah,
see
yeah,
it.
we see the
Yeah.
slides.
Okay, so in the truth, so the content of the presentation is, so basically we are trying to describe all our experience with the vacuum system of VIRGO, especially with the infrastructure and chambers and big parts that has to be built, for the vacuum system. And then we have a few hints, just a few hints for the Einstein telescope vacuum. Okay, so, and okay, so this is the content of the presentation. First, this is an aerial view of the VIRGO apparatus. Most of you know very well about that. Anyway, this is just to tell you that the vacuum system is divided, say, in two subsystems. Basically, we have the pipes, the 3-kilometer pipes that works at a pressure of a few in the range of the low 10 to minus 9 millibar, and what we call the, say, towers. So there are sort of chambers, big chambers at the extremities of each arm, and there the pressure level is around 10 to minus 80 millibar. Okay, and so here, okay, you have a look. This is the drawing that tries to give you a perspective of the sides. So this is a look of the vacuum chamber that are inside what we call the central area. That is the building, say, at the middle of the system. So there are big vertical chambers, the towers, 11 meter high and 2 meter wide. There are small, say, auxiliary chambers. You see these brown small chambers. There are these cryogenic pumps that Gianluca mentioned a few minutes before. There are, say, these, say, gold parts, and then there are the 3-kilometer tubes that you see clearly. Also, another component that is worth to be mentioned are the large valves that are big gate valves of 1 meter of diameter. And so then there are smaller cavities, smaller auxiliary cavities like the motor cleaner pipe, and now we have the squeezing pipe. Okay, so okay, this is a picture of that area, say, and you see what is the look of the vacuum chambers. So the area is quite crowded, yes, and so this chamber has the particularity to require a very clean environment, because the optics, you see on the bottom part of the picture, you see the one face of the assembly of one mirror. So these chambers are vertical and the access is from below. So in practice, these chambers are also used as clean room during the installation phases. And as all, they have also a lot of say recipes for cleanliness, electropolishing, pre-baking before the optics insertion, dust control, and also a clean airflow that is fundamental during the operation. Okay, it's a picture. Again, this you know very well. I think I've seen in other presentation. So concerning vacuum, these, say, towers, these vacuum chambers are divided in 2 or 3 compartments. There is one, what we call the upper part. This is the compartment that contains a lot of mechanics, cables. So you see a picture on the left. So where the vacuum has so we have to take compromises with vacuum, and the pressure is around 10 to the minus 6, 10 to the minus 7 millibar. Then we have, in some cases, we have a chamber of differential pumping, and then we have what we call the lower part, that is the part that contains the optics. You see the difference also looking by picture. So the lower part, as I said, is a sort of clean room, while the upper part is a high vacuum chambers. So they have to be connected, because to allow the passage of the suspension wire, you see this red line that I put in evidence here. So this wire pass through the whole tower, and so we have for this reason we have a sort of a small pipe that we call conductance pipe, that is used to reduce as much as possible the conductance between the two parts. In case this part could be pumped to reduce further the flow of gas between the upper and the lower part. Okay, one thing that is worth to say is that originally in VIRGO we were thinking to bake the lower part of the tower, even in a second stage. This idea with the optics inside, this idea was abandoned because really not practical, and even perhaps dangerous for the optics. And so from the vacuum point of view, a picture of a vacuum system. This is one tower. You see, these are our synoptic valves and pumps. Basically, we have so turbo pumps, dry pumps, various combination of gauges, residual gas analyzer. So one particularity is that we use dry pumps and magnetically suspended turbomolecular pumps to against the risk of contamination of lubricants or greases. Okay, another point quite important is the control system. All the data are integrated with the scientific data. Basically, we have, say, one control station per tower per vacuum system. So each, in fact, this I didn't say. Each say main chambers has its own completely independent pumping system to go from one bar to say to the working pressure. Okay, then is the pipe. So the first point is about the exceptionally large surface under vacuum, so 24,000 square meters. And so the pipe, in fact, is particular. I told you at the beginning of the presentation. So this is particularly another system. So there is nothing inside. It's just the beam, the laser beam, the main beam. The diameter 1.2 meter, and this is the tunnel, what we call tunnel. In the truth, this is a building, but it looks like a tunnel. This is is our, say, nickname. You see on the left a view on one extremity. That it's a particular place where there are, say, diaphragms made in glass, in absorbing glass. So that is okay. It's a particular place. Most of the pipe is completely empty. See, so the pipe is realized by welding different tube modules. Each module is 15 meters long. The pipe is made in classical 3 or 4L plain wool, cold rolled plain sheets, and so the very common material. Say. There is a bellows, maybe it's not clearly seen here in this drawing. So there is one bellows per module to allow the baking. In fact, we baked it at 150 degrees. There are only very few pumping ports, and so only very few flanges, auxiliary flange over the whole length. First, so last, but maybe the more important point is that with such a huge surface, we have to apply some treatment, conditioning treatment to reduce that casing. This is the air breakout treatment, essentially heating in air at 400 degrees for sort of 100 hours about. Okay. So our result about the gassing rate for hydrogen is sort of 3 × 10⁻14 millibar per second per square centimeter. Another detail is about the jointing between the modules that is done by welding. So this is an enlargement of what we call the lip joint. Then one sketch about the the baffle, that are the diaphragms that are welded inside the pipe. These are essentially stainless steel part. So from the point of view of the outgassing, it doesn't change very much the situation. Then a view of all the pipe components, rings, sheets, bellows. This maybe is more clear. That's a view of the workshop. So the workshop was really dedicated to these pipe constructions, and okay, yeah, perhaps so you can recognize that the quality of the cleanliness that is about 20 years ago. This photo, this picture is yes, is since that time, and okay, you see that the first point in the construction was considered the cleanliness and the control of cleanliness. Then a few words about the installation. So perhaps if you go back to the first picture. Okay, so the installation of the pipes was done passing through, so they were introduced in what we call the tunnel, passing from the middle of each arm. You see perhaps the pointer of my mouse. And okay, and they...
You have 5 minutes, Antonio.
Okay, so it's late. Okay, and so the rate was about, say, one per day, but this could be much increased, at least to 3 or 4 in case of, so when thinking about the 18 telescope, this was not the controlling rate of the system, of the vacuum system construction. Backout via DC current and Joule effect. Pumping system, only a few, you see from the picture that the red dots, this is really only a few pumping system, just exploiting the big conductance of the pipe, 1.2 meter in diameter. Cryogenic pumps, 1.2 meter, 1 meter in aperture and 2 meter long. These are installed in between the towers that are dominated by water and the pipes that where the pressure, as I told you, is about 10 times less, lower. Then the last piece is valves, large valves. They are really big. They are special construction. They are made in stainless steel that was again fired to reduce the outgassing rate. Okay, a short view on the cost of the vacuum system. In total, they were 1/3 of the cost of the total VIRGO apparatus. And the tube manufacturing was a larger part. So the contract was about, in that time, about 10 million euro, around 10 million euro. So this part. Okay, worth to mention that recently, 1 year ago in practice, the company made a study to renew the cost. So what is the cost? Now we know what is the cost of the same VIRGO tube if we have to rebuild it from scratch now. And roughly the cost is doubled. Okay, then several experience along the time, even difficulties. And then quickly, a few hints about the vacuum of ET. So the statistic of the pipes per detector. Okay, this table has been prepared by Andrea and Luca Paoli. So sort of 40 kilometers of pipes and several towers, many towers, an order of magnitude above the VIRGO towers, even of different and increased E8. And then about the pressure, we just made a few one example, one exercise, say. So considering the two detectors, we try to apply our requirement, that is that the gas tolerable in the pipes is so that the noise, the the related noise is a factor 3 below the minimum of the sensitivity. So applying this requirement, this is just an exercise, and for a say a typical gas composition, we got that for the high frequency pipe, we got an hydrogen pressure to compliant gas composition are for the frequency detector hydrogen 5 × 10⁻10 millibar, and say minor gases, water, CO, nitrogen at the level of 5 × 10⁻11. While for the low frequency one, so one could tolerate for the same composition a pressure that is about 10 times higher. Sorry. Okay. Then nothing special, just a few comments that you can read. Maybe later you can read yourself. The only point perhaps is the first that is worth to mention, that when thinking to the design the vacuum team, is very important to think about what are the last ultimate wanted performances from the vacuum system, since it's so in VIRGO, for instance, the initial VIRGO worked at 10⁻7 millibar. Now we are working at 10⁻9 millibar for the tubes. So it's important to plan well in advance what are the wanted ultimate performances. So okay, so for me it's enough. I finish it.
Thank you, Antonio. Thank you very much. Questions for Antonio or comments?
I have a question, if you want. Paolo Chigiotto from Serve.
Sure, Paolo, go ahead.
Thank you. Ciao, Antonio.
Ciao, ciao, ciao.
I have a question. When you discussed about the costs,
yes.
So sorry, I missed something. You said that the cost was for the present VIRGO, the total cost of the vacuum system was
1/3. So 1/3 of the total cost of the apparatus. So the total cost. So the cost of the VIRGO vacuum system, if I'm not wrong, was about 25 million euro. The pipe was 10.
VIRGO vacuum system, 25 million.
25, yes.
So now, if you had to build today, is the double? So it's 50 million.
But I mean the vacuum, the whole vacuum, the pipe 10.
Yeah, the whole vacuum system. So
for the pipe,
now,
yes.
If you want to scale up this value to the ET, how much? Where is the cost? Where do you?
If I consider the pipe, and I scale up to the ET, depending on the length of the pipe, so this is 3 kilo per meter. So it's more than 300 million for the pipe, only for the pipe.
Only for the pipe. Okay. Okay. Thank you very much.
Well, the vacuum system, besides the infrastructure, so the civil works for the infrastructure, is by far the most expensive item in the Einstein telescope business. Antonio, you said that the company that built the vacuum pipes for VIRGO reevaluated the costs, and that the outcome is that today it would cost 2 times as much.
Yes.
But where does this come from? Material, the manpower?
Yeah, in fact, say after the LIGO launch of the study, we got in touch with the company, and they kindly spent some time to do the study. Now, the cost of the raw material, at least for their process, is not much, so sort of 20%. So the cost of the raw material is not. I can provide the data, and there's no problem.
Okay, thank you.
Just to follow this argument, is it possible, Antonio, to have a breakdown of the costs as estimated by you or the company, in a way that we can see what are the main, the leading lines of the breakdown?
We can ask them. And with the, I think they are available because they, of course, they are interested. So we can ask them. Sure.
Okay. Thank you very much.
Yeah, Michele, you can go ahead. Before you go ahead, I remember that we had a breakdown of the costs in the ET design study. I don't remember on top of my mind the level of detail, but there was something there.
Yes, in fact, my comment was on that. So if you look at the T cost book, in the current cost book, the global cost of the vacuum system is 560 million of the vacuum system. And if you look into the old conceptual design report, there was a page at the end of the document with all the breakdown of all the costs. And in the current evaluation has been just updated for the inflation, not considering the change of cost of steel and something like that. So it's a very rough evaluation, but this is what we have now.
Sure. Anyway, the company was asked to build exactly VIRGO now, so they were not considering economies, increase of production rates. So it was just a baseline for estimate, to give you some data. So in case we could ask for further study and optimization. So I don't think this is really, if we build the pipe with that exactly with that industrial tool, I would say this is only a comparison.
Yeah, in any case, we say that you are in the ballpark of several hundreds million euros. Yeah, this is for sure. Okay, if there are no more questions or comments, let's thank Antonio again. Thank you, Antonio.
Yeah, but also there is a very good steel from China that now it's possible to buy. I mean, 304, 316, that is very good and not so expensive. So, okay, maybe we are going then in a political issue, but yeah, there is also this possibility that at the time was not available. Now China is producing coil of very good steel. So.
Okay. Shall we move on? Antonio, thank you again. The next speaker is Roberto Cemmino, a colleague from INFN, the National Labs in Frascati. Roberto is an expert of vacuum system for particle accelerator, actually, and he will speak about synergies between dynamic vacuum issues in accelerators and gravitational wave detectors.
Yes, first of all, let me thank the organizer to give me the possibility to tell you what are the results of some thinking we have done between our group in Frascati and people in Genova, which are of course working on VIRGO, and we need, for newcomers, I would say VIRGO is an essential flywheel for developing R&D that would be of interest also for ET. Anyway, so there are obviously, I'm not wasting too much time, there are clear synergies between for the vacuum cryogenic plants and installation between the ultimate accelerators, the big accelerators like LHC or AEC in this case, and gravitational wave observatories. Of course, there are a lot of recent research and development for the cryogenic dynamic vacuum. Are those issues of interest too? In fact, my first question when I approached this issue was, can a material and a surface science laboratory and a competence developed in recent years to tackle unconventional, I will explain later what I mean by that, dynamical vacuum be of some use for the running of existing gravitational wave interferometers and for the proposed one? Then I also have some I must say, if I can, what? It doesn't go. I have to go to next page, but it doesn't like. I don't know why. Maybe here. Okay, so there are also some personal motivation, because discussing this issue with colleagues, I got some very sharp comments. One was the only common items between LHC vacuum and the Einstein telescope are the pumps, which was a bit shocking. And a more general comment was that vacuuming accelerator has, of course, nothing to do with the one needed for the Einstein telescope, since there is not, the particle beam is not there, so it's only static vacuum is an issue and is of interest, while in ultimate accelerator, dynamic vacuum phenomena are dominating and are attracting most of the R&D effort, which is certainly true. And Paolo gave a fantastic talk showing you what are the overlaps between what I call the common standard vacuum issues, which are similar in gravitational wave interferometers and accelerators, pumps, diagnostic, and all the R&D between flanges, materials, coding, vacuum calculation, not to forget how important are vacuum calculation, which has been developed in a very strong way at CERN as well. Research and development on new material coating, use of negs and pumps, and so on and so forth. So we don't there's obvious overlaps between those topics. But I was looking around, and also thanks to discussion with people from VIRGO, I come to know that there are two very interesting, what I would call unconventional gravitational wave observatory issues, maybe vacuum issues or connected to vacuum. One could be is due to the fact that it has been observed that the mirrors will electrostatically charge. Both at VIRGO and advanced LIGO optics undergo to inhomogeneous electrostatic charging of variable and in fact unknown sign that may induce unwanted noise. And this is something that one should try to control, because the procedures that are undertaken for neutralization with positive or negative ions are certainly time consuming and in some cases also risky, because playing with ions is always an issue on very delicate cryosorption coatings on the mirror. Then there is another issue, which is a very interesting one. It is that cryosorption has been mentioned briefly in previous talks. Cryosorption on cold optics means that when your surface is cold, it will act as a pump, as a cryo pump, and will absorb frost and gas contamination with time. And of course, to cure it, the easiest idea is to warm it up, but that I would be worried to understand how time-consuming is this procedure. Are those two issues of any, let's say, of any overlap? Do they have any overlap with what we developed in our studies on accelerator dynamic vacuum? Well, I don't want to go through what it is unconventional issues in dynamic vacuum, but essentially it's the fact that the beam, we have a beam in the vacuum system that, for instance, when it's cold, LHC cold with the walls at 1.9 Kelvin, the vacuum is extremely ultra vacuum, better than 10 to minus 11 or so, because the wall is pumping everything in without the beam. But then you put the beam interact with vacuum chamber, induce impedance and induce desorption, electron yields, pressure runaways because of desorption, and produce electron. And the electron cloud formation is something I don't want to go to details. The only thing that I want to tell you here, and maybe there are some slides where you can take some deeper insight on the issue, is that in the system, like LHC, there are electrons which are produced by photoelectron, synchron radiation, desorption from the losses, residual gas ionization. But even I would add here electrons from ion pumps and gauges, which is somehow present in gravitational waves observatory towers and beam pipes that produce electrons. What do an electron? An electron, in fact, in this case, sees the beam passage, and get some energy from the beam, because in case of LHC, the beam is positive, or get repelled, but anyway, hit the wall. And he hit the wall and gets multiplied by what is called the secondary electron yield, which is the number of electrons emitted by the surface when hit by an electron of given energy, which is essentially what is the RT parameters now for the coronavirus pandemic. Is an indicator of how many electrons will get multiplied by each electron passage. This process can be in phase with the passage of the beam, and can multiply the electrons, can give rise to a multiplication, need to be mitigated. What is at the base of this process, as I said, is the secondary electron yield, which is the ratio between E out and E in, the current of electrons that are going out of the sample and the current out electrons that are going in. And you see that this shape is an interesting shape and depends on the energy of the primary electrons. And if you think that something of this kind happens on a dielectric like the mirror, VIRGO mirror or ET mirrors, of course, the charge left on the surface will depend on the energy of the impinging electrons. And this, in fact, is something that comes out from our experiments on, for instance, argon ice on copper, but there are also some literature results on oxides like aluminium 2 or oxide 3 or oxygen 3, thin layers, because otherwise it becomes very difficult to measure, but this is a different question. And you see from here then in a dielectric, in an insulator, the secondary electron yield is extremely high, but you always have a region in which the secondary electron yield is less than 1. So this, according to the energy that reaches of the electrons, that reaches your optic, you can very well explain the fact that the mirrors do charge electrostatically, and that it can happen in a way which is inhomogeneous, because it is where those electrons will hit, and the sign uncertainty is also explained by the energy difference of the electrons reaching your surface. But what is important here is that not only say the secondary electron yield, and this discussion here can explain the charging phenomena, but it's suggesting eventually how to cure it, because we can use electrons for a given low energy. We're talking about very low energy electrons, just above or below, say, keep in mind that above, say, you remove electrons from the surface, and below, say, you deposit electrons on the surface to neutralize the dielectric. And this is something which is ongoing and started thanks again to the flywheel role played by VIRGO, which is a running experiment now, which is dealing with these issues right now. And that is what we want to study, the secondary electron yield of representative materials from the mirrors, which is still in debate for the Einstein telescope, and to understand what is the curve we have to use to be below or above the secondary electron yield of 1. But not only that, I think we can, given this issue, this notion, we can think of charge the mirror locally by focusing on focusing a very low energy electron gun, and set a smart system to measure the effect of charging of the mirror. Because one of the issues in present mirrors is that people seem to see some effect, but they don't know where are the charges localized, what is the charge sign, and so on and so forth. So if you can produce and induce on a mock-up system this charge, you can then validate the approach and estimate the charging. Once this is all done, and it is clear that with a mock-up we can charge the mirror, but also discharge it in various regions. If this is validated, we can then try to think of moving this setup on an actual mirror. And this will allow us to neutralize this unwanted charge in UHV without entering the system, without putting high pressures of ions, neutralizing ions, and so that will reduce downtime. downtime time significantly. One other
You
issue,
have
which I
3
think,
more minutes, Roberto.
yes,
3
one
and a
other
half.
issue which I think is important is that on cryogenic mirrors, this method can be not only used to neutralize them, but to clean them. In fact, everybody knows that low temperature cryosol gas layer grows on mirrors, and as has been said, it will influence reflectivity and unwanted thermal noise. What is interesting here is that electrons are much more efficient than photons to desorb gases. Here you have the desorption yield of CO and CO2, but water is more or less studied, and the electrons are much less penetrating. I show here the mean free path of an electron in a solid surface, and you see that at the electron energy we may consider of about 100 electron volt, the penetration that is less than 10 angstroms, which means that if you are bothered by a layer of few microns, you can heat the surface with electrons without touching at all the mirrors, and so we be sure not to damage them. If you do some back of the envelope calculation, assuming an effective pressure of 10 to minus 10, but you can change it, and to discuss this effective pressure, we'll need another seminar, I guess. You assume you have a one monolayer, assume a sticking coefficient of one monolayer is going to be absorbed in 10,000 seconds. But then if you want to remove it by electrons, you may need a milliamp current per centimeter square, and 1 second will be enough to remove this monolayer deposited, which is 10 to the 4 faster, 10 to the 3, 10 to the 2 faster, according to how much current you want to allow to deposit on the surface. What is interesting here is that the total power deposited on this process is not particularly significant. And if this effect works, you can clean your dirt, your frost from your surface in UHV with marginal heating up of the mirror and possibly much reduced downtime, because warming up a 10 Kelvin mirror suspended by 2 meters, 3 millimeter diameter wires, it probably will take a long time. So I think this issue again as well deserves further investigation. We have a lab in Frascati, which is a material and surface science laboratory with 2 state-of-the-art, which we set up where we can keep the sample at below 20 Kelvin and study it with all the surface techniques available in a lab. And with minor upgrade, we can continue and we can do some proof of principle secondary electron yield for the charging and the study of mirror materials at room temperature and low temperature before and after cryoabsorption of gases, of course on small samples. And I conclude saying that, of course, as we have seen, there are many conventional vacuum issues in common between gravitational wave observatory and accelerators, but there are also some unconventional vacuum studies, which are sort of vacuum studies by history more than by let's say by nature. But anyway, at CERN, I mean, this has been studied in the vacuum department, so we call it vacuum studies where both community can still learn from each other. There is a lot of research and development is ahead, and there would be important to tackle it as soon as possible to include in the final design the correct solution. And of course, as Frascati, we will see, but we are eager and very happy to contribute if needed to this, to solve some of those challenges or to study some of those challenges. Thanks a lot for attention. I finish here.
Thank you very much, Roberto. We have time for a few questions. So there is one in the chat from Riccardo. I can read it. How many electron volts are needed for secondary electron yield? Because,
as I said, we are studying it right now, but the trade-off between secondary electron yield below 1 and above 1 depends on the material. On insulators could become very quickly, very soon, but we're talking about 10 eV 200 eV electrons. In copper, metallic copper is this onset happens at about 200 eV. So we are talking about really low energy electrons.
I don't know if Ricardo wants to comment on this.
Yeah, I don't know what would be on a dielectric, in fact, but on the coating, even tens of electron volts or a few electron volts may cause color center that then require annealing to anneal out. So one would have to be very, very careful.
This is for sure, but one thing is that this is for sure something that, as written here, we have to study. No, to study the effect of electrons on mirror surface. What makes me I cannot say it makes me optimistic, but electrons hit your surface anyway because your surface charges up. So if that is only inducing charging but not destroying your surfaces or not inducing the color centers formation, that is already a good indication. Keep in mind one thing that, as I said, electrons are very low penetrating power. They do not penetrate in the matter, so they will stay on the surface, and even at room temperature your surface has a layer of contaminants on top. So one has to be to study this issue. Is one of the issues which is important, but in respect to ions and photons, which are known to penetrate much longer, much more, and to interact with the coatings, electrons may be advantageous. Of course, this is, I think, is the right time to raise R&D questions, not to give solutions, right? So it would be nice to study, of course, on the quality of the surface by electron bombardment eventually.
I did not say it's impossible. I just said that there are pretty nice risks where deeply evaluated.
I think everything you do to a mirror of 200 kilo, so complicated, is a risky bit. Even venting it and go close to it with a neutralizer, as it is now done apparently in VIRGO. So everything has to be considered. Yeah, sure.
There is a question from Albert.
Yes, Roberto, this is Albert Lazzarini from LIGO. We have developed a discharge system for our test masses to address the issue that you identified.
Yeah.
And it's based on a corona discharge of gas at very low energy that then is entrained in neutral gas, and we raise the pressure in the chambers to a few torr.
Yeah.
And ionized, we can change the polarity of the ionization and address either positive or negative charging in the mirrors pretty effectively.
Yeah, I know that, but again, I don't know how long would it takes you to do a complete neutralization cycle, which because you anyway have to put your tanks in 10 to minus in few millibars. So one has to see whether this method works at all, because we are just approaching and proposing it as a R&D study. But in case it works, it will be done in 10 to minus 10 in the pressure where the mirror is sitting. So we will never influence the vacuum. So possibly the recovery time from this operation would be extremely fast. I don't know about advanced LIGO now. How long does it take to neutralize those optics?
It's at least a day process to stop operations and discharge the mirror and then come back.
Okay, so it's not that bad eventually. So you're pumping quickly, but yes, if that, yeah, okay, yeah. But yeah, fine. But okay. What you are probably doing is you're not controlling, but you're producing low energy electrons, you're producing low energy ions. What I'm telling you is that to neutralize with positive charge, you don't need necessarily ions. You can use electrons which are producing more electrons from the surface, which are pulling out electrons. That's all. That's all makes that's all the difference. Is in fact
Understood.
The two methods. In fact, you don't need to switch to ions or change polarity or try to guess where and so. And what is nice of this method, in fact, if it works at all, of course, is that you can design a mock-up to study exactly what is the signal you obtain on the noise or whatever when you are depositing so much current, so much electrons on a patch on your mirror. This would be extremely, because you go blind essentially. You put whatever in your system and it will neutralize everything. But would be nice to understand if what is actually the effect of a small or a distributed charge on the mirror that on a mock-up system. And of course, with an electron gun, controlled electron gun, you may more or less guess where you're hitting and how much you are delivering, and you can then see if you can build up a feedback. So to know when your mirror is neutral, because that is another question. You do your process and you hope your mirror is neutral, which is fine. It happens to be like that, but it's a bit. It would be nice to be sure that the signal that you can, let's say, you can induce the detrimental signal you want to remove, because then you know when it's on or when it's off. That's what we came up.
I'm sorry, but I think we have to interrupt this discussion, which is very interesting. Just the start of a discussion, of course, which can continue offline as well. Let's thank again Roberto for the nice talk. Thanks. And let's move on to the last speaker of the day and of the symposium, by the way, who is Albert Lazzarini from Caltech and Deputy Director of LIGO Laboratory. He's going to talk about the R&D plans for the Cosmic Explorer vacuum infrastructure. Thank you very much, Albert.
Thank you, Gianluca, and organizers. Thank you. Thank you. Can you see my slide?
Very well. Yes.
Okay. Thank you very much for asking me to give a presentation, and thank you for accommodating the Pacific time zone with your last talk of the last day, which is at a good time for me. So I have a brief presentation just outlining what our plans are in the United States for Cosmic Explorer vacuum infrastructure R&D. The genesis of the work that began last year in January, there was a large vacuum workshop that was hosted by LIGO and supported by the National Science Foundation, and we invited our collaborators from around the world to participate. And the goal was to begin an examination of the vacuum design concepts that are needed to go to a large-scale system of many kilometers, such as Cosmic Explorer or Einstein telescope. There were about 38 people who attended the workshop. It lasted several days, and the proceedings are public. And I have the URL listed on this slide that one can go and see what the results of the workshop were. The workshop, we organized it in a number of working groups addressing various topics. Conventional single wall vacuum designs, continuing the concept that was used for both VIRGO and LIGO in terms of the initial generation instruments, but looking at how one might reduce costs. There was non-conventional technology that was also looked at involving multiple shelled systems and addressing questions of whether or not one can pre-treat the material that's going to be used to make the vacuum tubes in such a way to reduce the water uptake, which is ultimately the big challenge to achieving UHV levels that are needed for operations in laser interferometers. And then, of course, over 40 kilometers or tens of kilometers for ET, addressing how you're going to do distributed pumping. We haven't had to do distributed pumping at LIGO. We pump from the two ends because the conductance is such that we could use large cryo pumps at either end of the 4-kilometer beam tubes, and that is adequate to keep the system under acceptable levels of water outgassing pressure. This is definitely not going to be the case when one deals with tens of kilometers. So the path forward coming out of the workshop was to start looking at tests and conceptualization for these novel vacuum tube designs. One thing that was decided that it was worth doing was looking at materials other than stainless steel from both cost and hydrogen outgassing concerns. And if one went with a nested system, how cheaply could one make the outer vessel itself to reduce cost? And then looking at what kind of coatings might one put on the inside of the beam tubes to reduce water adsorption, as I mentioned earlier. And a number of our colleagues from National Institutes of Science and Technology in the United States, Thomas Jefferson Nuclear Lab here in the United States, and also CERN and Fermilab participated in a workshop. CERN offered to host a second workshop this past April, but of course, with the ongoing world pandemic, that did not take place, although we hope that once people can travel again, that we will resume. So our vacuum infrastructure R&D, the main motivation is to find ways to significantly reduce the cost of producing about 80 kilometers of ultra-high vacuum beam tubes. Initial LIGO, if we were simply to scale up that approach, we estimate in 2028 dollars that we would be looking at about $650 million just for the vacuum beam tube, not to mention the rest of the infrastructure for building a large interferometer. So this motivates us to look at how to do this less expensively. It turns out, since we built initial LIGO, low carbon steel materials may turn out to be acceptable in terms of their outgassing properties. Also, because of the reduced cost, one can consider going to thicker beam tube walls, much thicker than what we have now, and that has various advantages for us. The other thing we want to look at is how to not have to carry out an in situ high temperature bakeout, which we did at LIGO. This itself would cost order tens of millions of dollars on the scale of Cosmic Explorer. And if the beam tube wall thickness is sufficiently large, we feel it might be possible not to have the expensive concrete covers that LIGO installed over the beam tubes in its first generation. All these things taken together promise to reduce the estimated cost of just the beam tube infrastructure by as much as 40%, which is an attractive factor to drive the R&D that we're talking about here. The program that we put together follows from the findings and recommendations from the workshop that I just mentioned. And we recently submitted a proposal in collaboration with from LIGO Laboratory, Caltech, and MIT, with collaborators from the Department of Energy. CERN has agreed to participate, and the National Institute of Standards is also participating. And we have another university, College of William and Mary, that's participating through Jefferson Lab. So the dual requirements that we face are minimizing the system cost while maintaining the stringent UHV requirements that we've heard discussed both earlier presentations. And the primary requirement is to reduce and limit the column density of residual gas that leads to phase noise of the laser propagating down these long beam tubes. And the table that I have here is derived from a phase noise model that was published back in the middle 90s by Mike Zucker and Stan Whitcomb. And what it shows is that the more massive the molecular species that's in the tube, the more deleterious the effect on the phase noise, and that's shown in the column, in the central column called ratio to H2, where it's normalized to the effect of the phase noise effect of hydrogen. And so this is the reason that motivates us to make sure that we have very clean systems. Heavy hydrocarbons typically introduced during the fabrication of steel are really an issue, and so the tubes have to be very, very clean. And ultimately, water is the dominant species that competes with hydrogen for phase noise effects, and it's because of its higher molecular weight, contributes by a factor of 3 for the same pressure compared to what hydrogen does. So the research areas that we are pursuing follow from the recommendations of the workshop, as I mentioned. We're exploring carbon and alloy steels as a material rather than stainless. There have been a number of reported low outgassing rates for these materials based on modern technologies that are used to produce steel in the foundries. Paolo gave a presentation, I think it was yesterday, indicating some preliminary measurements that they have been doing on some of these materials, motivated by the workshop that took place last year. So we want to identify surface processing, alloy, and coatings to reduce environmental effect, corrosion on the exterior surfaces. Since we're dealing with non-stainless steel materials, we have to worry about the environment much more than is the case for stainless. We intend to perform a test of a substantial section, 10 to 20 meters of beam tube that we procure, and assess its performance under UHV conditions. We will have to deal with welding in the field, and so we want to explore welding techniques for these, especially if we go to thicker steel material, thicker wall values than we used in initial LIGO. And ultimately, the idea is to also engage industry to identify steel mills that have the capability to maybe accommodate some of our unique requirements, given the scale of the order that would be for the procurement for the beam tubes. It might be possible to have dedicated steel mills that can produce this material for us. Secondly, we're looking at techniques to eliminate the high temperature bakeout that I mentioned earlier. We're looking for coatings that could be applied to the inner surface of the steel, excuse me, to reduce water adsorption. Silicon-based and other hydrophobic coatings are of interest here, and potential steel alloy modifications that affect the surface adhesion properties of water to the bare metal. I have a slide on the next. The next slide will show some of these things. Also exploring whether we can do low temperature, longer duration bakes than we did to reduce the overall cost of the bake. And ultimately also looking at whether it's possible, in case we need a vent, to introduce ultra dry gas refills that will allow the system to come back down to adequate pressures much more quickly after the initial bake. We have facilities at Caltech that can be used for these types of experiments. And one concept that we're exploring is to develop a moving external heater with a dry gas flush technique that would be used to bake out the tube in very short segments as a propagating bake out without having to do the full multi-kilometer heating of the tubes that we did in the initial LIGO. So these are some models. Ray Weiss did these calculations for us at what the promise is for hydrophobic coatings. And it uses the Dubinin-Radoshevich model that was developed back in the late 40s in the USSR at the time for molecular absorption. And it's been used successfully over many years and validated with our beam tube vacuum performance. And what this slide shows is that the binding energy of water on the surface of uncoated stainless steel is typically 1 eV, which is 10,000 Kelvin. But if you can reduce that binding energy to a quarter of its value, and that's something that appears to be the case with hydrophobic materials such as silicon, one gets a much more rapid decrease in the ambient water pressure in the tubes, as one pumps on the system compared to the very slow 1/T drop off that one sees with standard surfaces. Also, it's, as I mentioned, it's possible if one considers doing low temperature bakes. This is a model for a 2-kilometer section of tube showing the drop off, the initial heating of the tube, and then the very rapid drop off when it's brought back to temperatures that are ambient. We're also going to look at alternative geometries, and this is a nested system that I mentioned earlier, using as inexpensive as possible exterior tube with potentially a very thin-walled inner aluminum tube. It would operate, the outer system would operate at industrial vacuums, while the inner one would be used to maintain UHV, and there's a sketch on the next page. We intend to consult with industrial experts, companies that have designed our gate valves in the past, to look at how to build large aperture shutters that would be needed for these systems, especially the nested system. It requires an invention of a new valving concept. And ultimately, the output of this would be a conceptual design for the beam tube subsystem for a cosmic explorer, and it would inform a follow-on engineering study where one would want to build a larger scale section of tube representative of the final system. So this is a simple schematic showing how a nested tube concept might look. There's an outer system of steel. There's radiation shields to isolate thermal diurnal excursions from the inside of the system, which is then a relatively thin-walled aluminum tube with expansion joints and baffling systems. And then embedded inside the inner system would be non-evaporable getters, zirconium aluminum oxide pumping systems, so that we would not have to have mechanical or cryo pumping systems distributed along the tube. And such modules could be introduced by at rather frequent intervals along the tube, which would provide very good pumping over long periods of time. So in such a system, if a nested system, one has to deal with the fact that at some point one has to equilibrate the pressure between the inside and the outside if we have a thin-walled material, both in the initial pump down and in case we need to vent. And so one is looking at coming up with novel concepts for remotely actuatable axial valves that open and close to connect and communicate the internal and the external systems. The program we envision will last about 3 years. It's intense. The first year will be dedicated to exploratory work, investigating and identifying suitable mills and vendors and coatings, looking and making multiple redundant outgassing measurements on samples that would be obtained from vendors, exploring welding compatibilities that need to be dealt with in joining dissimilar metals that will be required in such a system, and developing concepts, as I mentioned earlier, for large aperture valves. The last 2 years we'll continue the working on the valve concepts, and then we're going to undertake 2 large-scale experiments at the 2 LIGO observatories. At LIGO Hanford, we're looking at comparing the performance of 2 10-meter sections of commercial tube, one coated, one uncoated, to look at the outgassing property differentials. And at Livingston, we're planning to introduce a 20-meter section of tube, and the effort there will focus on the moving heater concept that was mentioned earlier. Ultimately, in the second year, we'll do a down selection of the various options that we've identified, and then flesh out a conceptual design of the 40-kilometer UHV system that will inform follow-on studies. There's the task that I outlined in the earlier part of my talk will be done. Some are serial and some are in parallel, but ultimately it's addressing materials, bakeouts, alternative geometries, and novel gate valve techniques. And the various studies then will inform a down selection, which will go into the conceptual design, as I mentioned earlier. So in closing, we're looking at a three-year R&D program in collaboration with the U.S. Department of Energy. CERN is participating, the National Institutes of Standard and Technology in the United States, and the College of William and Mary. We've designed a series of investigations that are aimed at finding ways to significantly reduce the cost of 80 kilometers of beam tube that will be required while maintaining the strict UHV characteristics that are necessary here. And as I mentioned, this will culminate in a conceptual design to inform follow-on engineering studies for the actual vacuum infrastructure of Cosmic Explorer. We defer to the follow-on study the need to address scattered light control in these very long beam tubes that are a relatively narrow diameter. And this includes addressing optical properties of the beam tube surfaces themselves. The initial LIGO, we air bake the systems. We have an oxidized patina on the inside of the beam tubes, which has good optical properties in terms of absorption and reflectivity. We're not looking at that in the initial, in this 3-year study. We're focusing on materials for cost-effective production of beam tubes. We will have to deal with baffling at some point, of course, and this will be especially important if one considers going to longer wavelengths where the surfaces are smoother, and more importantly, one has to actually worry about forward scattering through diffraction processes of the beam tube propagating down. Even a 1 to 1.5 meter beam tube has noticeable effects on a 2-micron beam by virtue of diffraction effects. That's all I have to present. Thank you for the opportunity.
Thank you very much. Thank you very much, Albert. Very interesting talk. We are almost at the end of the day and of the symposium, but we have time for a few questions to Albert.
Gianluca?
Fulvio, go ahead.
Ciao Albert.
Ciao.
Just one question, simple. Concerning this idea of annular valves, this is just a conceptual design, what we have shown, or there are already attempts to build one prototype?
No, these are just artist concepts at this point, Fulvio.
Okay.
That's what we want to do. And in particular, Ken Mason, whom you may know from MIT, who has been very involved with valve designs for initial LIGO and some of our valve repairs, is particularly interested in exploring this concept.
Thanks.
Sure.
Any more comments or questions? I have one, maybe you said it, I just didn't get it. The 3-year R&D program is already funded, or it's still a
No, we've just recently submitted the proposal to the NSF. We're hopeful that we'll be funded. The time scale is such that typically the time between a submission and a arrival of funding is such that we would be expecting money next July.
Okay.
Thank you.
Any more questions? If not, I think we can close the session. Let's thank again Albert and all the other speakers. We are at the end of the symposium, and I think that Michele wants to give a very short closing remark.
Yeah, thanks for all the 46 people that are still connected. I think it has been very, and in addition, the people that are on YouTube, because we are not counting them, but they are not negligible. So I think it has been a very interesting workshop, symposium, and it has been the largest by far with respect to the others. We achieved hundreds of people connected, considering Zoom and YouTube. And I think it has been incredibly interesting with many presentations with new people and new subjects. In fact, what I really appreciated is the fact that there are new persons in the T under the T radar. So we have groups that are coming from different institutions, but also from different countries. For example, we saw today talk about the silicon fibers. This is a very promising situation for the T, and makes us very to have a large hope for the next future. And I think everybody understood that for the next future we have a huge amount of work to do. I mean, the discussion today on governance show what is the difficulty to realize an efficient project that should run in the next few years at an incredible speed, but also involving a large scientific community. I think that these are the two apparently conflicting requirements: large community and fast and efficient project. But we need to find a way to conjugate these two requirements. And I believe that this will be an incredible challenge for the steering committee that has to fill the gap from today to the next months, when we will see growing up the collaboration. And I want to make a very warm invitation to everybody to react to what has been said this morning about the submission of your proposal in terms of participation to the Einstein telescope, because we really need in the next weeks, in the next months, a contribution from everybody. I'm really satisfied of this meeting, but I'm also incredibly satisfied by the wonderful support from LAP for this meeting, because it has been efficient. We had no problems on generally, not only for the connection, well organized. So thanks to lab people, in particular Edwige, that she made incredible work for that, and made this meeting very, very efficient, and I think successful. So that's all what I want to say. I don't know if Harald is connected. He wants to add a few words. Voila, Harald is connected. So please, Harald.
Yeah, not much to add from my side. You said everything. It was a very pleasant meeting, lots of new impressions, lots of new people especially, which is very pleasing to see that so many new people are now joining with new expertise, with their enthusiasm, and that is really good to see. And I would also like to thank Edwige and her team for the good organization. No technical problems at all. Well, no problems at all. Thanks a lot, Edwige, and thanks to all the participants who still remained until now.
Okay, so we can close this meeting, but you will listen us very soon, because we will start to contact people for all the boards that we are forming, and for all the work that we need to do in the next weeks. Okay, bye-bye, everybody.
Bye-bye. Thank you.
Bye. Bye-bye.